Okay, so we are live. Today's topic is ratio problems in the math section. We just got done talking about the rules and the guidelines as usual. So let's kick it off. All right, this problem is data sufficiency. Again, make sure you know how data sufficiency works. If you don't, at least try to follow along with us. And most importantly, don't forget where the multiple choice answers are found. Here is where those are. I'll give you about a minute and a half, 2 minutes to do this problem. Okay, we still only have about 28 or so answers out of 43 people here. So remember, you got to pick something. There's only so much I can nag you about this kind of thing, but remember the way this test works. There's absolutely no such thing as not answering a question. So you have to pick something that is a thing, and you have to answer the question. Even if you're guessing, the GMAT doesn't let you leave things blank. So go ahead and pick something. We got 5 more seconds to make a guess. Okay, so here's what we have so far. Again, if you are Cody, I see your name listed up there. If you are here listening in, then maybe you can help this user whose name is Sparkles, who's having tech issues. I don't know if you're actually live, Dave, so let's try to help there. Okay, so notice that there are several responses of C and several of E. If you are in the non-response group here, again, make sure that you pick something. Always pick a thing. So, well, unless you, of course, you can't see the question. But okay, so let's talk about it. On a certain sightseeing tour, the ratio of the number of women to the number of children was 5 to 2. What was the number of men on the sightseeing tour? Background here, with every data sufficiency question in the whole world, with any of these problems, before you get started, the first thing you want to do is figure out specifically what sufficient and not sufficient mean. And in most of these cases, you should try to define what not sufficient is first. So figure out, or translate is more like it. Translate sufficient and not sufficient into the specifics of the problem. So when it comes to questions where you have to find a number like this one, you can just use this template if you're not used to the way this works yet. You can always just fill in this box. Not sufficient means I can find different values for the thing I'm trying to find. And then sufficient means I can't, and I'm stuck with a single value for that. So in this case, the thing we're trying to find is the number of men. So you can just fill in this template with the number of men. The number of men, and then the number of men. And then notice that usually not sufficient is what winds up being your goal here. Your goal is actually to get not sufficient. So that's the strategy in the vast majority of data sufficiency problems is that your goal is actually to try to get 2 different things to happen here. So in this case, not sufficient. So we're trying for. If we can get different values, then we're good. So the ratio of the number of children to the number of men. So we know that women to children is 5 to 2. Statement 1, someone tell me a story about statement 1. Like, notice that we're given a ratio of 5 to 2 for W to C. Statement 1 just tells us that C to M is 5 to 11. Notice that we just have a bunch of ratios here. So someone tell me a story about that. Because there were a few people who thought that statement 1 was sufficient here. So, well, remember the goal. We don't really want to do a ton of work that we don't have to do. So, do we have to do any work here? Is the question. Remember, not sufficient means I can get different values for a number here. If I just have ratios and I don't have anything else, then what does that mean? It's close, Ginny, it's close to what you're saying there. It's not any value because the ratios are still going to restrict the value in some sense. But you have the right idea. You have where I'm going with this is that you can get any size of number at all because it's a ratio. So that's because a lot of you guys are talking about how to do the algebra here. And if you just have statement 1, there's absolutely no reason to do any algebra because you have a goal, which is can I get 2 different values? If all you have is ratios and you don't have any other conditions, then you can always get any multiple of that ratio. If all you have is ratios, you can always get infinite possibilities. Because that's how ratios work. You have no idea how big the numbers are. You just know what their relative sizes are. So this is not sufficient. If you use our grid device, then we have A, B, B, C, and we can kill AD. Varun says men are not mentioned. Well, they are. I mean, they're in statement 1, so you at least have to think about that much, because this is a thing. Statement 2, men are not mentioned, if that's where you're going with this. So, yeah, we can also eliminate statement 2 very quickly. One person actually said B to this problem, B like boy. Maybe that was just a random guess or a mistake or something, but it should be clear that statement 2 is not sufficient. So there's no mention of men at all. So there could be anything at all. So it could be any value whatsoever. Not sufficient. Okay. So what about the combination of the 2 statements? So now we need to worry about combining these statements because this is a restriction. And when you have a restriction, that's going to mess with data sufficiency here. So, Cody looks like, Sparkle looks like you got your answer there. It's probably not the answer you want, but Cody thinks. Okay, so we got to combine the statements. Both statements are insufficient, so we have to combine them. Let's talk about how to do that. So combined, we know that, yeah, so Sarah says you can combine the ratios so that they are equal for the kids. That's pretty much the idea. The kids, because those are that's the element that we have in common between the 2 ratios. So the background fact that you should understand about ratios here is that you can actually multiply a ratio by any number you want as long as you multiply both sides. Because remember, a ratio at the end of the day is a fraction. So you can multiply both sides of a ratio by whatever number. So if you need to put 2 ratios together, it's a lot like making a common denominator, except it's not a common denominator. So making 2 ratios compatible with each other is like making a common denominator. Just think of it as the same process, except you just have to look at which element of the ratio is in common between the two parts. So here we have W to C is 5 to 2, and then C to M is 5 to 11. So what helps here is just to line that all up. So we know that this is 5 to 2, and we know that this is supposed to be 5 to 11. So this is a lot like making a common denominator where these are your denominators to start with. So the common denominator there is 10. So you can multiply that by, that's the same as saying 25 to 10. So we can do this again over here. We can multiply both of these by 5. That'll create a 10 in the box. So now it's 25 to 10. And then we can multiply these by 2. That'll create 10 to 22. So your overall ratio is 25 to 10 to 22. So what? Remember, it's data sufficiency. And also remember that these are not random, meaningless variables. I mean, these are actually numbers of people. So that's going to affect the outcome here. Varun, it looks like you got converted into a heart there. So I love you too. Yeah, you have to use the condition that women are less than 30. So how do you do this in general when there are whole numbers? Let's go ahead and take this onto another page just so that we have room to discuss. So new page. There's your problem. Remember, we're looking at the two statements together. What we just discovered is that women to children to 10 is 25 to 10 to 22. So how do you deal with whole numbers in general when there are whole numbers, especially in a data sufficiency problem? You're just going to have to, you're going to have to basically list out the possibilities, because algebra, the problem here is that, if you just do algebra, there's no way of telling what the whole number possibilities are. Because, I mean, if you're doing algebra, these could be like 25 square root 2, 10 square root 2, and 22 square root 2. So if you are restricted to whole numbers, then you should definitely just make lists of possibilities. Because algebra doesn't have any tools that actually distinguish between whole numbers and not whole numbers. Like, there's nothing, I mean, algebra is awesome and can do lots of things, but there's nothing in the algebra toolkit that deals with the distinction between integer and non-integer. So the algebra is not really going to be your friend here. But what you can do is just list out possibilities. So there you go. It doesn't take too long here, because remember, you have to have an integer multiple of this ratio. So here we could have actually 25 women, 10 children, and 22 men. But what would be the next possibility in this ratio? Like, what would be the next item in our list? Yeah, the next item in our list would be everything times 2, and then everything times 3, and so on. But if you look at this, we're already looking at too many people, because we already have 50 women, and we have to be under 30. So that's a pretty short list. So this can't work. This can't work. This is the only possibility. And so we're done. Any questions about that? If you have a question, go ahead and type it in the box. Let's see. Yeah, good. So again, there were a lot of people who picked E here. If you picked E, what probably happened was that you just looked at this as some sort of weird algebra problem rather than as whole numbers of people. So as far as takeaways that you can get from this, can I explain the last bit? What last bit? Go ahead and tell me which last bit you're talking about. takeaways that you can get, first of all, make sure you know how to combine ratios. Again, it's like making a common denominator. So if you know how to make a common denominator, you also know how to do this. So same process. And then also don't forget when you deal with whole numbers. Don't be afraid to make a list. As you can see, you're probably not going to have to make a very long list. So how we zeroed in on the answer, well, that seems to be the entire process here. So, I mean, the short summary would be, okay, we have this ratio. The only way we can get whole numbers of all these things is if we have a multiple of this. So we could have 1 times this, we could have 2 times this, etc. Nothing in between. If you don't see why, then try to get numbers in between these and see what happens. And so then all of the possibilities are too big, except for this. So, yeah. Okay, any other questions? Okay. All right, cool. Statement 2 said, yeah, if it said 50 women or fewer, then it would be insufficient. And then insignificant, if you're thinking that C is a trap answer here, then what you're doing is you're expanding the idea of a trap answer way too much. I mean, trap answer means that there is literally no work, and you can just see right away by doing like simple arithmetic at most. You know, like here you actually have to combine the ratios to get C, so this is clearly not a trap answer. I mean, you know, this is not a trivial step. So, right, it's not so obvious. I mean, you know, combining ratios is a step that a lot of people don't know how to do. Like a C trap is when you're just like, oh, I have this number and I have this other number. So just be aware that's not really a thing. Okay, good. Let's look at another one. So this one, the challenge is probably going to be the word problem aspect of it more so than the ratio aspect. But give this a shot. Let's see if you can do it within a reasonable amount of time. So more than 2 minutes, because again, it's a word problem and you have to get through the words. But there you go. Make sure you know where the multiple choice answers are. That's where they are. Okay. Have fun. Okay, so go ahead and pick something that is a thing here. Of the people who have answers, most of you guys are right, but there are still a lot of people who don't have answers. So it's been about 3 minutes at this point, so we should hang it up and talk about it. Okay, there's still almost 10 non-responders. So if you are a non-responder, please pick a thing. Oh, and also don't click your answer twice. If you have an answer already indicated, then if you click it again, it'll just erase the answer that you have. So, okay. While we finish this up, again, this is a word problem, so I mean it does involve ratios, but the main issue here for most people is probably the organization of the word problem. So for word problems, the deal here is you want to first understand what's in the problem. First read, you don't do any math yet. Don't do math yet. Just understand what's in the problem. And then organize it. And once you have an organization going on here, then go back the second time and do math. So you want to organize this first. Don't do any math yet the first time. Organize it. And I mean, this might seem weird, but if it seems weird, it's only because you're thinking in like a classroom kind of way, because in the real world, this is basically how people do everything. I mean, if you were going to do taxes with a spreadsheet, you would not start calculating things before you had a spreadsheet. You would make a spreadsheet that was empty, and then you would calculate things in it after you had made it. So same sort of thing here. And then as far as organization of these things goes, here is, for this one I put 3 minutes as the timer because it's a longer problem than usual. So remember, make sure you're thinking along the same lines. If a problem has more words and more stuff, then it's perfectly okay to put more than average time on it. So, okay. And by the way, here's a guideline. Here's kind of a no fuss, no BS guideline for whether you guys have sufficient organization when you do these problems. So a good guideline to follow. When you organize these problems, if you ever have to look at the words in the prompt again, you are not organized enough. Your work is not sufficiently organized. Like once you have a chart or some sort of system going on for this, even if it's just equations, then that's going to be sort of hard, but if you can get that to work, then good. But once you have something, whether it's a chart or a table or a system of equations, you shouldn't really ever have to look at the prompt ever again. If you do, then that means that you aren't as organized as you could be. So let's talk about that. We want to get this into some sort of organized form, and then once we are there, we don't ever want to have to look at this again, because that's the point here, right? So, okay. So what are the things in the problem? Well, we have a fuel oil bill for February and January. And then we notice what we have. We don't just have a fuel bill for those months. What do we also have? Like for each month, we have the fuel bill that Alex actually paid. And then what else do we have? Chat box. We have the if part. Yeah, so we have like a hypothetical, right? So like what's in the problem is the first guideline here. So we should do. Well, we have actual fuel bills for January and February. And then we have hypothetical fuel bills for those same months. Because if it had been, here's what would have happened. So we can just make a chart for this. This is certainly not the only way to organize it, but we can do columns for February and January, and then we can do actual and hypothetical. And I looked at February before January, which seems a little bit weird perhaps, but notice the way they gave you was February to January. So it makes more sense to do it in this sort of way because that way we don't have to reverse the words that are in the problem. So, and then we also want to get everything on this chart so that we want to make sure we never have to keep looking back up at the prompt. So the ratio of the actual fuel bills was 3 to 2 in this order, February to January. So that needs to be 3 to 2. We should write that down so that we don't have to look back up at it. The hypothetical is 40 more for February. So February is January plus 40 in this row. And then the ratio here is also 5 to 3. Okay, once we have that, we do not ever, and once we look at one more thing, which is what is the actual goal of the problem. This is the actual goal of the problem. Once we have that, we don't ever again have to look at the prompt. It's just totally not a thing. So we can actually just black out that part. This is a sign of whether you are organized enough. If you can do that, then you win. Why is February, January plus 40? Because look at this. When you're talking about hypotheticals, if the fuel oil bill had been 40 more, sorry, it's 40 more than it was. So that's wrong. You're right. February is actual. Thank you. It's hypothetical February is actual February. See, I'm just testing you guys to see if you're paying attention. So Jagdish is paying attention. So is Varun. And so is Chini. Thanks. Okay, so now we can black that out for real. There. So this is actually more like this column. So let's move that over. Okay, there. This is why you want to get all this out of the way, right? Because you guys corrected me on this one, but the point is if you use your whole brain power to figure this stuff out before you dive into the work, you're much more likely to figure these things out correctly. So if you're trying to do that while you're trying to wrangle with math, it's a lot harder to get that to work. So, okay. Now let's talk about how to do this. Does anybody know how you can do this without using any algebra? Remember, one of your main goals on this stuff is to try to figure out multiple ways of solving the problems. So yeah, right, non-algebra solution. When we say plug numbers, we're talking about making up your own values, which is not something you can really do here. But yeah, plugging from the answer choices. So back solve. Remember what back solve is. It means you plug in an answer choice. And then once you have that, you just do whatever work you can do. You don't need a master plan. It's kind of nice. You can just work your way through the math. And then if everything agrees, then that's sufficient. Or so not sufficient. Then you have a correct answer. So this, let me make that smaller so it doesn't run into it. Okay. That's how backsolve works. So let's just start from an answer choice. Remember that you don't want to make like a million charts. So when you backsolve, make sure you don't take up the entire cell of your chart with your number. So let's say that we started with, I don't know, I like $300. That's a nice number, so let's start with something like that. Remember, the goal is to start with numbers that are nice to work with. So that would be $300 in the goal box. Where is somewhere we could go from there? Yeah, you can go to actual February. And then notice the other thing that we should write down here that we didn't is there's a relationship for January, too. We're just talking about if we had changed the February bill, but there's no mention of changing the January bill. So the hypothetical January bill is the same as the real January bill. So hypothetical January equals real January. Okay, so yeah, we can just do this ratio. Make sure you can do these ratios without having to set up proportions and put a variable in there, because that's just kind of inefficient and you don't want to do it. When you have a ratio, you can just multiply the ratio by something, and that will give you these numbers. So this time we're multiplying by 150 to give this, so 3 times 150 is 450. So 450. Where's somewhere we can go from there? Anything you can do, right? We have relationships between actual and hypothetical. Yeah, so the hypothetical February bill, you'd add 490. So yeah, you get 40. You'd add 42. You get 490. The hypothetical January bill is the same as the real one. And then we can check this. Well, this is not a ratio of 5 to 3. You know, it's kind of close, but it's just not really there. We're off by about $10 here. If we had 500 to 300, then it would work. So let's say we tried, And now that you've tried a choice, note that trying further choices is incredibly efficient because you're just going to be doing the exact same thing that you just did. So if you don't know whether to go up or down, it's not obvious whether we should go up or down here. So let's just try another choice. Let's try something like C. Okay, well, if that's 360, then we're multiplying this ratio by 180. So that would be 540. Add $40. Leave it the same. So if this were a 360, if this was a 5-to-3 ratio, this would have to be 600. So we'd be multiplying by 120. So now we are $20 short here. Last time we were $10 short. That means we're going in the wrong direction. So that means the answer is almost certainly going to be A. But as long as we're doing this, we might as well just C. So let's try A. So that would be a 240 here. That means we're multiplying by 120. So 360. 360 plus $40 is $400. This stays the same as 240, and this works because 3 times 80 is 240, and 5 times the same 80 is 400. So we have a winner. So again, make sure that back solving is a thing in your arsenal. Even if you got this problem to work with an algebraic approach, when you go back and study it, review it, make sure you get other approaches to it, including the back solving. Any questions about this? Okay. So let's talk about an algebra solution. And remember, by the way, all we have to take over this page is our work. Because once we have enough organization, again, there's no reason to even take the problem statement along with that. So there's again a test of whether you are organized enough. So let's erase the content of the boxes and let's talk about an algebra solution this time. So the content of the boxes is okay. So now let's talk about an algebra solution. So when you set up ratios algebraically, how many variables should you use? Yeah, 1. That's the key point here, right? Like, don't use 2 variables if you don't need 2 variables. So when you have a given ratio, use 1 variable. Because that's the point of a ratio, right? The point of a ratio is that it's the same number times all of those things in the ratio. So for instance, if you have a ratio of 3 to 4, then think about what that means. Again, it could be like 3 and 4, it could be 6 and 8, it could be 3 square root 2 and 4 square root 2. We don't know, but it's going to be 3 times a number, and then it's going to be 4 times the exact same number. So we can just call this, the quantities in the ratio are 3x and 4x. And I mean, this applies to ratios of absolutely any number of things. So if you have 5 things that are in a ratio of 1 to 2 to 3 to 4 to 5, you can still use a single variable for all of that. So in this case, your quantities are in that ratio are going to be x, 2x, 3x, 4x, and 5x. You don't really need more than 1 variable unless you have some extra amount of uncertainty here. So we can start off with either of these things. Let's say we start off with that one. So we can just let this be 3x, and we can let this be 2x. Now what can we do with those? Notice if we've marked up our chart, that the chart almost tells us what to do. Like the problem literally almost solves itself at this point. That's the nice thing about being organized. You don't have to think anymore. Yeah, the hypothetical here is $40 plus the actual, so you just add $40 to it. And then here the hypothetical is the same as the actual, so 2x. Now, if you already have quantities, that's when you set up a proportion. So if you're not defining a variable. So notice the different things here. With the 3 to 2, we're actually defining the meaning of what x is. Like we don't have anything at all, so we have to make a variable. So if you are defining a variable, but if you already have quantities, if you already have variables or numbers, because we could call these things 3y and 5y, but we don't really want to because we have stuff. We have 3x plus 40 and we have 2x. So then put the existing quantities into a proportion, which is those, you make one fraction equal to another fraction. So in this case, that is going to be, the existing ratio is 5 to 3. And then that is going to be the proportion of these two quantities. So this is going to be 3x plus 40 on top, and this is going to be 2x on the bottom. And there you have it. So you can solve this. This is a pretty standard issue, cross-multiply type of deal. So you get 10x equals 9x plus 120. So if you subtract 9x, you get x is 120. But then we don't want 120, we want 2x, so that's 240. So there you go. The answer is 2x, which is 240. Okay, so just notice the takeaways here. There are quite a few of them. The first is you should not have to keep looking back up at the words. So if you got this, but you took a really long time to do it, then that's probably what the issue is. It probably was you had to keep looking back up at this black hole. I mean, remember, words are not really your friend. I mean, you know, there's not really a lot of other options besides words if you want to say something, so we have to say them. But you want to get out of the words and into an organized setup as soon as possible. So write everything down. Just write it all down. If you have to uncover the black thing, you should have written down more stuff. If you do that, you'll be much more efficient because everything is right there. Secondly, make sure you know how to back solve. Third, make sure you know how to set all this stuff up with algebra. Any questions? It looks like someone is typing, so I can wait a second to see if you're typing. I mean, the deal here is this. This is a very, very general thing. Like anything that is in words at all, anything, if you express the problem in words, no matter whether it's ratio, we don't care if it's ratios. If it's words, we want to get it out of words, basically. Words, you want to translate the words into a more friendly form, which means more organized. I mean, notice once we have that, just notice how much more efficient we are. I mean, you can probably solve this problem without a chart, but it'll just take you a longer time. How do you get better at it? I mean, again, see, the thing is, this is not really a skill that you don't have. I mean, if you guys were running a business and you had to make a spreadsheet for your expenses, I trust that all of you could do that. I mean, you would just figure out how to do it. You would just be like, okay, here are my expenses. Here is what I should put on my columns, and then like months on the rows. You'd get it. It would happen. I mean, not everyone would make the spreadsheet in the same way, but you would all come up with a way to make the spreadsheet. So, I mean, classrooms are weird. When people think of this as academic, they're like, oh my gosh, I'm helpless, and somebody has to tell me how to make this chart. Not so. I mean, just think about it like making the same sort of chart in the real world, and it will make sense. So, like, in other words, we shouldn't have to tell you how to make a chart. Just look at the stuff in the problem, and whatever's in there, just figure out some way to organize it. Just So once you understand what's there, it's not a thing that we had to have in our heads ahead of time. I mean, we have actual for 2 months and we have hypothetical for 2 months. So this is pretty intuitive. I mean, again, this is not the only way that you could make this, but it's a convenient way. So just do it and it'll become a habit is basically the idea. Any other questions? No, let's take a look at this. Go for it. This problem is actually from our CAT exam. Okay, there's a lot of words in this problem again, so I'll give you more than the average time. Go for it. Okay, if you need a little bit more time, then take it. But if you, at this point, it's been about 3 minutes. So if you are not definitely getting somewhere with this, then you should guess. Okay, we still have some non-responders here. So if you don't have something at this point, go ahead and just make a guess. Here's what we are kind of all over the place on this one. Here are your responses so far. Again, we still have 9 non-responders. One of the non-responders is me, but the other 8. Remember, you can't sit there and stare at these problems. You have to say something soon enough here. So there's not a lot of signal here. We have almost equal representation of these answers. So let's check that out. So again, let's organize it. So what's in the problem? Well, so what's going on here? Well, you have wins and losses for the first n games. You also have wins and losses for the last n games, and those are together. Those are the whole season, basically. So you have wins and losses, and then you have total, basically. So. And then notice that at the end, you don't really need a column for all the totals because you can just add it up at the end. So the way we can organize this is we can say, one way we can organize it at least is the first n games and then the last n games. And then for those things, we just have wins, we have losses, and then we have the total. In this case is a thing that we're dealing with because that's the n in the end. So, all right. And notice you don't have to call them because you might be thinking, if you're thinking to yourself, hey, I don't really need n and n, then that's a good thing to be thinking because you really don't need both of those. All of this stuff is tied together. So let's write out enough stuff so that we don't have to keep referring to this. So, look, because again, all of this organizing stuff is before you even look at math. We don't even have to decide how we're going to do it until we have it organized. We don't have to decide whether we're going to do algebra or something else. Those decisions are all things that happen later. So in the first n games, we know that wins to losses here is 1 to 2. And then we know that in this part, the wins to losses is 1 to 3. And then we know that this ratio is 4 to 5. That doesn't mean they are literally 4 and 5, but just notice that this is a ratio. So, however you want to notate these things on your chart, just do it. But just make sure you don't have to keep referring to stuff. And then you want, the ultimate goal of the problem here is the ratio of these two numbers. So, of the ratio of wins to losses. So total, I guess we can go ahead and make another row for that. So wins to losses. Total. Okay, so this is the total of all the games. And the goal is the ratio of these two things, the wins to losses. That ratio is the goal. So once you have this kind of situation, there's a lot of stuff happening here, but this ratio is the goal of the problem. And there it is. And again, now we honestly don't have to ever, again, look at the words. So let's just not look at the words. And notice that the letters M and N are not really necessarily things here. You can do something else there. But let's talk about a non-algebra solution first. How can you do this without algebra? I mean, notice that all you have is ratios, which means we're not ever going to find out how many games were played, because everything is just ratios. So what can you do? And you just multiply 4/5 times wins and losses and add. Well, let's see. I mean, let's see what happens when we just proceed through this and have some sort of organized approach. I mean, there's no concrete numbers. Well, what can you do in situations where there are no concrete numbers? Yeah, you can pick numbers. So let's pick our own and then see if that works. So pick your own values. Okay. Now here, picking values is going to be a little tricky because there are a lot of conditions to satisfy. But make sure when you're picking values, you're going to need to think about the way these things interact, right? So if these are 1 to 2 up there in that first row, then what you need to think about is that overall we're looking at like 1/3 and 2/3 of the total. So one takeaway that you should be able to get here, yeah, that's where we're ultimately getting with this. But make sure you know how to be comfortable going back and forth between converting between fractions and ratios. Ratios, and I guess I'll call them component fractions. For instance, if you have a 1 to 2 ratio of wins to losses, that means that it's like the 1 and the 2, the total is 3, which means that 1/3 of those games are wins and 2/3 of those games are losses. So if wins to losses is 1 to 2, then 1/3 of the games are wins and 2/3 are losses. In general, it's the number over the sum of all of them. So if it's if you had this kind of ratio here, 1 to 2 to 3 to 4 to 5, then 1 plus 2 plus 3 plus 4 plus 5 is 15. So this quantity would be 1/15 of the whole thing. This would be 2/15 of the whole thing. This would be 3/15 of the whole thing, and so forth. So make sure you can do that, because that's going to help us pick numbers if we know that relationship. So in the first row, the wins here are 1/3 of the total. And not the total, but the total for that row, and then the 2/3 of the total for the losses. 1-to-3 ratio means that these are 1/4 of your total, and 2 3/4 of your total. So if you think about the numbers we have to pick, because here's the deal. We have to pick 4 to 5, but we also want these thirds and fourths to work out. So like if we want the thirds to work out, as Varun says, we can try multiples of, we can try 12 and 15. Remember, we need some multiple of 4 and 5. So if we do the 12, then the thirds work out nicely, but the 15 still doesn't really work with these. And again, notice if you just write all of this stuff down, then you can very quickly see what it is that you need. So these don't work with the fourths, so we can also multiply them by 4. So let's do that. So then we can use 48 and 60, and then everything works. So I mean, that's the hard part here. The hard part is coming up with those numbers. But if you are organized and if you have the conditions written down, it's much less hard. So then 1/3 of 48 would be 16 wins. 2/3 of 48 would be 32 losses. 1/4 of 60 is 15 wins. 3/4 of 60 is 45 losses. So we have a total of 31 wins and 77 losses. And so the answer is E, like elephant. There it is. So again, notice the role of organization here. Like if we take the time to just set this up, I mean, even if it takes you a really long time to do that, it's totally worth it. Because once you have a decent organizational framework, then a lot of these problems will effectively solve themselves, which is a very nice situation indeed. Any questions about this? I mean, nothing will be wrong with it. We're going to look at algebra here in a second. But again, one of your primary goals here would be one of everybody's primary goals here should be to come up with other solutions. Like algebra should not be the only game in town here. So, okay, let's look at this as an algebra problem. So why didn't we multiply with 4 and 5? Does anybody know the answer to that question? I'm assuming you're talking about those 4 and 5. And it seems like you're asking about doing something like what we did here. So why is that not a thing in this case? It's not a thing because, I mean, a couple of you guys are trying to type it. It's not a thing because these are actually independent ratios. Like this is not a combined ratio. These are not the same wins and the same losses here. Like these are different entities. Like in the problem about the road trip, there was one number of women and one number of men and one number of children. So you were looking at two ratios of ultimately the same quantity. But these are not the same things. Like these are totally different numbers of wins. Like if you have trouble remembering that, you could always call them like W sub 1 and W sub 2 or something. But these are not the same quantities, so you can't do the same thing because they're different numbers. So let's talk about doing this algebraically. So if we do this algebraically, then let's start from this. You don't have to, but you certainly can, right? So, and remember that let's type the same things on there that we did before. So this is 1/3 of the total in that box. And this is 2/3 of the total. And then here, this is 1/4 of the total in this row. And this is 3/4 of that total. Okay. So, what do we call two things in a ratio of 4 to 5? Let me make this bigger. There. Two things in a 4 to 5 ratio, we can call them what? I mean, same as any other ratio, 4 to 5, at least to get started here. We can call them 4x and 5x. Again, remember that much at least should be an instinct. And then, because the deal is, once you have that, again, this problem has a lot of things going on in it, but that part of the setup should be pretty much automatic. So if we want to do this, we can't really be afraid of fractions. 1/3 of x is, so we want 1/3 of that total, which is 4x. So that's going to be 1/3 of 4x, which is equal to 4/3 x. I'm going to import these fractions from another program, so you'll see them magically appear on the board. So 1/3 of this thing here is 4/3 x. That's how you get this box. So 4/3 x in that box. And then similarly, it's 2/3 of 4x, which is going to be 8/3 x in the other box. So you can also write them as 4x over 3 and 8x over 3, sure, totally. So that's that as well. And then we can do the same sort of thing here if we have 1/4 of 5x. Then that's going to be 5/4 x. And then 3/4 of 5x is going to be 15/4 x. So again, if you're afraid of fractions, you would probably want to, well, if you're afraid of fractions, the first thing that you should take from that is that you should practice fractions so that you are not afraid of them anymore. But in this problem, if you didn't like the fractions, you should, in the immediate future, just try plugging in numbers. But then go back and practice the fraction type stuff just so that you're not, afraid of it. So there we go. And then the total of all the wins is you just make a common denominator, right? So 4/3 plus 4/3 plus 5/4 is the same thing as you make 12ths out of that. So it's 16/12 plus 15/12. So that is how you get this total. It's just adding fractions, right? So that's where this comes from. So that's going to be 16 plus 15 is 31/12. So that's 31/12 x. Notice we can do this whole thing with just x. I mean, we don't even need the m and the n here because we don't need them. I mean, it's a ratio problem, and everything is in terms of one quantity. So we don't even need the names that they gave them. And then if you add 8/3 x and 15/4 x, then this one will give you 77/12 x. So that is, and then if you look at that ratio, I mean, you don't have to put those into a fraction, right? If you look at that ratio, you can tell that the ratio is 31 to 77. Um, I still don't understand how first. We're not told that it's a half. This is a ratio. The Stewart. Make sure you don't. This is what we talked about in the previous thing, right? Make sure you can convert between ratios and component fractions. So this is a ratio of 1 to 2. It's not 1/2 of the total. It's a 1 to 2 ratio. So I mean, if this is not clear, then what you want to do is, like let's say you had a ratio where the first number was bigger. So like this. If I told you boys to girls in some sort of situation is 4 to 3, I mean, okay, what should be obvious here is that 4/3 of the people are not boys, because you can't have more than 1 as a fraction. But the way you think about this, I mean, imagine if you literally had 4 boys and 3 girls. You don't have to actually have those numbers. You could have 8 and 6 or 400 and 300. But when you find fractions of these, you want to just think about the simplest numbers. So the total of those is 7. And I mean, that means that you have 4 out of 7 boys. So 4/7 of everyone is boys, and 3/7 of everyone is going to be girls. So just make sure you can go back and forth between these. Because again, this is a 1 to 2 ratio. This is not 1/2 of anything. This is 1 win for every 2 losses. So that means that out of every 3 games, 1 is a win and 2 is a loss. So hopefully that helps. So there's a question here. If any of you guys have listened to more than a couple of these programs, you're going to know what my answer to this is. But does anybody know what my answer to that is? See, a couple of you guys are typing. Yeah, know how to do both ways. And that's the point, right? Exactly. Just know how to do both of them. When you review the problem, your goal is to just figure out as many ways as you can to solve these things. So be equally comfortable with both. Because you're going to encounter some problems where you kind of have to do one or the other. So, and then if you think of something, try it. And then if you get stuck, try something else. Absolutely the worst thing you could do to yourself here would be to try to remember some sort of hierarchy of these methods. Like, in other words, if you think you're always going to try, I don't know, algebra before plugging, the problem is that you might just never try plugging. I mean, if you ever rank things as like number 1 method and number 2 reserve method, then realistically speaking, what that probably means is that you just won't try method number 2. So everything is number 1, everything. Like plugging in numbers here is number 1, and algebra here is also number 1. Everything is A1 priority. You want to have as many tools in your box as you can. I mean, it's kind of like doing anything else, right? Like if you're a babysitter and you want to get a kid to calm down, you should just have lots of ways to get a kid to calm down. You shouldn't have like, oh, this is the best way. Because what if it doesn't work? Then you just have to have more ways. Same sort of deal. Okay. Let's try to do one more problem before we break. How about this? Let's see. This one shouldn't be too bad if you ever make stuff in the kitchen. But when you're looking at this problem, again, if a problem is a real world situation, then don't forget about the real world when you solve these things. Give this a shot. Again, make sure you remember where multiple choice thingies are found. Go for it. Okay, let's wrap it up here and pick an answer, please. Yeah, we got about 40 people here, and there's only about 25 responses, so let's make it happen. Okay. So again, if you don't have an answer, I can't, necessarily make you have one, but the GMAT doesn't let you not answer the problems. So make sure you're answering the problems. We seem to be pretty good on this one as a group, although there are still lots of other responses. We have a majority here, but there's still lots of people picking other answers. So let's take a look. I mean, again, let's at least organize in some sort of way here. So, like, what's going on is we have cans of concentrate, and then we use those to make juice. So, what's in the problem? Well, just think about what quantities we're dealing with, right? We have cans of concentrate. That's a thing. How many cans of concentrate? So that should be a quantity. Also, they also mentioned that there are 12 ounces in a can. So that's ounces in each can. And then, 206 ounce servings. They don't mention servings anywhere else, so you should pretty much know right away that you want to change that into just 1,200 ounces. So, because they don't do anything else with it, so it should be pretty clear what and we should do all this before we think about mathematics itself. Let's just simplify. That's 1,200 ounces. So that's also the total ounces of juice. Okay. So, and then how many cans of the concentrate? So let's just think about the thought process. Again, your organizational device doesn't have to be a chart, but you should at least think about what the thought process is. So we start with ounces of juice. And then we're going to go from ounces of juice to, what does ounces of juice relate to? Like, where are we going to go from there? We're going to go from ounces of juice to, well, you can't go straight to the number of cans because the cans are not cans of juice. The cans are cans of the concentrated frozen stuff. So we have to go to ounces of what first? This is not the only way, but if you start from ounces of juice, then you can go to ounces of concentrate. And then once you have that, you can go to cans. So now let's start doing math. So yeah, that's basically the deal, Varun, in terms of like, but if you don't have that, then you don't have that. So let's talk about the thought process. To go from ounces of concentrate to cans, there are 12 ounces in each can. So this is just going to be division by 12 to give you the number of cans. But how do you do this step? Like, what's the relationship between ounces of juice and ounces of concentrate? Notice that you have to interpret the statement that is here. And remember, when you see these statements, you have to interpret them in the way that makes sense on planet Earth. So, you can make certain assumptions about how these things mix together. So it's not 1 to 3 because 1 to 3 is not the ratio of juice to anything. The juice is the combination of the 1 and the 3. So like notice that the juice is actually that you mix the water and the concentrate together. So the juice comes from the water and the concentrate. And I mean, you don't want to think about, volume changes and stuff. I mean, if you were a chemist, you would be like, oh, it's not exactly 4. But, I mean, unless they actually tell you something like that, you just want to assume the volumes add up when you throw them in the same container. So this means that for every 1 unit of concentrate, you get 4 units of juice. So the amount of juice is going to be 4 times the amount of concentrate. And I mean, again, we don't care about the water because they don't ask us about the water. That's why we, at least in your head, you should at least think about that. That's the relationship that we care about. So the 3/4 would be the water, but we don't really care. So, because they don't ask us about it. So shines, that's why we don't do 3/4. I mean, if they asked us about water, then they wouldn't care, right? So this is 1,200 ounces. So this would be 300 ounces. And so then you would divide that by 12, and you get 25 cans. So there you go. It's a thing. You can also back solve this thing, right? Like if you don't want to solve it in the forward direction, you can always just back solve. So let's say we start, because I mean back solving you don't need as much of a plan. That's the primary advantage of back solving is you can kind of just pick a choice and then watch where it goes. You can just kind of see what falls out of it. And that was the previous discussion. You have to put the juice and the concentrate together to make juice. You have to put the water and the concentrate together. So these 1 can and 3 cans gives you 4 cans of juice. If you want to back solve, we can, like, let's say we start from C because it's a nice number. Let's say 50 cans of concentrate. So we still have to figure out the same relationship. So that's each can of that gives you 12 ounces. So 600 ounces of concentrate. And then that's times 4 for the juice. So that times 4 is 2,400 ounces of juice. And I mean, notice that's not too hard. And we don't even need to keep plugging because this is exactly twice what we want. So that means that the correct answer is just going to be half of 50. So 25 cans. So you can back solve, you can forward solve, you can, do that. Okay, I mean, again, as far as questions like this go, if you have thoughts like this, I mean, it's not totally unreasonable to think something like this, but if you have thoughts like this, you should very quickly realize that if that is a thing, then it would be impossible to solve the problem. So just, if you have thoughts like this, just think about what the consequences are. So if that's what they meant, then the problem is impossible. And they are clearly not going to give you a problem that is impossible. So you should think, okay, what am I not interpreting in the way that I have to? So find another interpretation. So there you go. If there's no unit except ounces, then the ounces have to be a thing. So, okay, this question here, we gotta wrap up pretty soon, but as far as this question goes, this question that's here. Okay, when you're practicing problems, like the best answer I can give you to that would be, remember to make the distinction between doing the problem for the first time, which is under time conditions, and then reviewing the problem, which is under not time conditions. I mean, these are very different things. I mean, when you are doing the problems, you should always, do them within a time constraint that is reasonably in line with what you'll be dealing with. So, I mean, if it's a word problem, it doesn't have to be strictly 2 minutes, because remember that, it's an average. You can go over above it. But, try to solve all the problems in line with real time constraints on the test. But then when you review the problem, then it's unlimited. That's the point of review, is spend all the time you want and try to find as many different approaches as possible. And I mean, if something is slow or labor intensive, that's when you want to mess with it. But you don't, at the same time, you want to always reinforce timing conditions at first. So when you later go back, that's another story, but you have to teach yourself to stay on pace here. Okay, we gotta quit here. Thank you guys for attending. The next edition of this is, let's see, I want to say it's not for more than 2 weeks, but you can check the page, and the page will tell you. Because let's see, it might actually be in 2 weeks. I don't know the schedule off the top of my head, but I do know there's only one more of these in the month of December, and then we'll take a break from it until mid-January. So check the page, and then, yeah. Okay. I don't ever decide the subject for next time until it's about an hour before. So there's no advance notice of that. Okay, we're gonna wrap up here. Thanks, guys, and have a great week. Good night and goodbye.